Yeah, there we go. So welcome to the next lecture and at the same time the last lecture where we plan to talk about symmetric primitives. And at the same time, it's also the lecture where we are trying to take our deepest dive yet into why primitives look the way they are. So the topic for today is design and cryptanalysis strategies for symmetric primitives and in particular for block ciphers. Because the lecture is quite stuffed with content today, I've skipped the quiz this time. If you do prefer to have a quiz in the future, maybe drop me a comment so that I know what your preferences are for the next few times. So, what is the plan for today? As I said, it's quite a schedule. First, we want to look at some general design principles. In the very first lecture on symmetric primitives, we already mentioned the first few principles, namely the concepts of confusion and diffusion. And today I want to define both of those a bit more specifically by introducing both the concept of nonlinearity as well as the so-called avalanche effect, which are two very classic notions for the security of block ciphers. And at the same time, they're also going to serve as an introduction for having a look at a more modern cryptanalysis approach, namely differential cryptanalysis, which we will see is quite closely related to these more classical concepts, but is still today one of the two most important analysis techniques for block ciphers. And it guides the design of every block cipher that is published today, as well as every permutation, tweakable block cipher, and so on. And since this is a bit of an involved concept, we're for the most part going to focus on applying it to a toy cipher when we explain the attack. So don't worry, this is not going to look like a secure cipher, but the good thing is the mechanisms work in exactly the same way for larger ciphers. And for a toy cipher, it's easier to understand things like the differential distribution table and the so-called differential characteristics that make up the main concepts of this attack approach. And in the final third of the lecture, we're going to have a look at how block ciphers defend against this attack. And more specifically, we're going to have a closer look at how the block cipher AES manages this protection. And the general strategy that AES uses here is called the wide trail design strategy. So let's first start with some general principles, and we can actually trace several of them back to way before the first currently known block ciphers were published, namely back to Claude Shannon, who already defined some of these principles in around 1945, so way before the first block ciphers that we still know today were actually defined. So some of these concepts are from the 40s, but the first public implementation of it that looks anything like modern ciphers is from the 70s. So Shannon was quite a bit ahead of his time. So to recap a bit what we already heard about the design of block ciphers. We already saw that in order to construct such a mapping which translates the message to the cipher text based on the key, we have a number of design principles that guide us. And the first principle, which defines a sort of goal we want to achieve, is the so-called Shannon principle, which says that a requirement for the security of this cipher is that each input bit and each key bit must influence each output bit in a complicated way. And this actually jumbles several concepts into one thing. So first, this relationship should be complicated, which is also sometimes phrased as confusion. More classically, the description here was that the influence of each key bit on each output bit must be complicated and hard to invert. This is meant by confusion. And then we have diffusion, which originally in Shannon's sense meant that every input bit should influence as many output bits as possible. So the effect of a small change of the input should be turned into a big impact on the output. And this is what we mean by diffusion. And some of the original design principles how to achieve this are also due to Shannon. So in particular, there is the concept of an iterated cipher, which essentially any block cipher that we know today belongs in this category. And by this we mean that we have a simple round function that we repeat many times, so that we only have to implement a simple circuit and still get a secure thing overall. And more specifically, this round function usually combines several different steps. This is a concept called product cipher, meaning the cipher or the operation is a product of many different individual operations. And this is also a concept due to Shannon. So he already said that it's possible to combine different permutations which are not themselves secure, but by the combination, the total is stronger than the individual parts. And one of the most classical choices of these different operations is given by the SPN construction, where each round consists first of an XOR of the key, or the round key, which already happens before the round, and then two operations of the round itself, namely a substitution step and a permutation or mixing step, where the substitution is a small operation, so only with a local impact, like an S-box lookup, but it should have strong properties and be a nonlinear function to contribute towards confusion. So the nonlinearity is here equated with confusion, in the meaning of having a complicated relationship. And next we have this permutation step or mixing step, which is supposed to achieve diffusion. So the idea here is that the permutation step is something that affects a larger part of the block, for example, by shuffling the bits, but at the same time it can be a relatively easy step. It's okay if this step is a linear function, for example. So these are the general ingredients that we want to take into account. So let's have a closer look at these two layers. First, at the substitution layer, the nonlinear layer that we have. And usually this simply means that we take all the bits of our intermediate state and we group it in blocks and put each block into our S box, which is simply a small lookup table. Or it can also be implemented as a circuit, but in any case it takes a small selection of bits and translates it into in a complicated way into some output, such that it's in the case of SPNs an invertible function, meaning every output also occurs only exactly once for one of the possible inputs. So it looks approximately like illustrated here on top. We have in this case 8 S boxes, and each of these S boxes in the example is a 4-bit S box, which translates every 4-bit character into another 4-bit character. Now, what do we require from this operation? We say that it must provide nonlinearity. Let's first question why that is, or what would happen if it were not a nonlinear function, but if it were a linear function. In that case, the entire cipher would be linear, because we already said that the other operation, the mixing layer, is linear. So if both the mixing layer and the S-box were linear, then our entire cipher could be described by linear equations. In particular, the output could always be written as some linear function of the input plus some linear function of the key. So we would get a sort of linear equation system where every output bit is a combination of some plaintext bits and some key bits. And if we have such a simple linear equation system where the number of variables is only the size of the key and the number of equations we have is either 1 times the ciphertext size, if we have just one such combination, or if we learn more plaintext ciphertext combinations, we can arbitrarily increase the number of equations we have. And as soon as the number of equations we have is at least as much as the key size, we can simply solve this system by applying something like Gaussian elimination to it. So this would mean that if the complete cipher were linear, we could easily find out the key as soon as we have one or a few plain text ciphertext combinations that we know. Which would obviously be a very bad idea, because collecting such combinations is usually not too difficult. Because very often we know at least part of the plain text, because we know, for example, the text follows a particular format. So if we use it in a picture like here above, where the encryption works in this direction and the decryption works backwards, then the S-box must be invertible, meaning that the outputs here are a permutation of all possible 4-bit values, so every value occurs exactly once. This is not necessarily if we use this building block in a Feistel network. But for this lecture, we're going to focus on the SPN case. So in that case, this is always an invertible function. So we already said that being linear is a bad idea, but the question is, how can we measure nonlinearity? So how do we quantify how nonlinear something is? And there are actually different metrics related to this nonlinearity, but I will pick out the one that we usually refer to as nonlinearity. And what this metric measures is how far away is a particular function from the closest linear function. So in other words, if I try to approximate the function by a linear function, how far off is it? And by asking how far off is it, you shouldn't imagine this like you know, from when you draw a graph and you have something like a linear function is a line and a nonlinear function could be like quadratic, for example. So you have a large distance of the individual points from the closest line. This is not really what we mean here, because we're talking about bits, so we also need to measure the distance with respect to these bits. And we can do this as follows. So the definition I've given here is not really for a function like a block cipher, but for a simpler object. So it's for an object that is a function that maps some bits to one output bit. We also call such an object or such a function a Boolean function. Now, this is not exactly what a block cipher looks like, because a block cipher maps many bits to many bits. Such a many-to-many bit function is also called a vectorial Boolean function. But the good thing is that many of the things we define for a single bit can also be generalized to many bits. So let's first focus on this simpler object with just one output bit. And then nonlinearity is defined as follows. So first we define the linearity. This is the maximum distance that the closest linear function has from our function. So f is the function we want to evaluate, and g is the best approximation that is a linear function. And by a good approximation, what we mean is it matches our function on as many inputs as possible. So for as many values of these n input bits here, which we call x, the output of our original function should be the same as this linear function here. So to recall, both of these output 1 bit, and if this 1 bit is the same, we say that it adds 1 to the linearity, and if it's not the same, if it's an error or a difference, then we don't count it. And the nonlinearity is then simply the inverse of that, so 1 minus the linearity. So to clarify this a bit, let's illustrate it with some examples. So first, let's have a look at the following example function, f0, which takes 4 input bits and produces 1 output bit. We can see from the formula given here that this is a linear function because the output is a linear combination of the inputs. Then the nonlinearity of this f is 1, or in other words, the linearity is 1. Nonlinearity is 0. How can we see this? Well, we can find a very good linear approximation of our function, namely simply the function itself. So this is a linear function, and it is a good approximation because it matches our function on every possible input. That's great. So here, this is a very simple example. Let's have a look at a more interesting, definitely not linear function, namely at the function f1 here, which we define as f of abcd equals a like before plus the product of all the input bits. Now, at first glance, this looks like it's a very, very nonlinear function, right? Because it has a very high degree. It has a degree of 4. However, it turns out that this function is actually not that nonlinear. Why is that? This is because for almost all possible values of a, b, c, d, this part here is actually 0. Because as soon as at least one of the bits here is 0, this one here is also 0. Which means that a good approximation for this function is if we say that we approximate this part here by 0. So the approximation function would be just g equals the first input a. So actually the same one that we had before here. Now this is a very, very good approximation of this function here because it matches the output on all inputs except one. Namely on the one where all of these bits are set to 1. In that case, our approximation was wrong, but in all other cases, it was correct. So despite looking very nonlinear, this function is actually not very nonlinear at all, and we can easily approximate it. Now finally, another example that looks not so nonlinear, but that is much more nonlinear than the above, namely the function a times b plus c times d. Maybe a comment on the notation here. I'm using here the notation of the finite field f2. So addition and multiplication modulo 2, which means that addition is simply an XOR and multiplication is the same as an AND. Because 0 times 0 is 0, 0 times 1 is 0, and vice versa, and 1 times 1 is 1, which is exactly the same function as an AND. So this is a notation that follows more the mathematical field object. We could instead also write an XOR, so a plus with a circle here, and an AND, so a wedge shape here for these multiplications. And it would mean exactly the same thing. By the way, this representation here, so writing a Boolean function using only plus and times is also called the algebraic normal form of this function. From logic, you might know things like the disjunctive normal form and the conjunctive normal forms, which uses an OR and an AND and a NOT. But for cryptography, it's actually more often useful to use this algebraic normal form, which uses XOR and AND. Okay, so back to our function here, which was a times b plus c times d. What is a good approximation of this? There are actually several equally good approximations that you can find. I've just picked out the simplest here. And I've picked it by knowing that a times b is most often 0, and c times d is also most often 0 in 3 out of 4 cases. And 0 plus 0 is also 0. So approximating this by 0 is a reasonably good approximation. So when is it wrong? It's wrong when at least one of the two terms here equals 1. So either if a and b are 1, or if c and d are 1, but not if all of them are 1. So in total, there are 6 cases where we make an error in this approximation, but in 10 out of the 16 cases, our approximation is correct. Okay, so this is the most nonlinear of these functions according to the nonlinearity concept. However, there are of course also other concepts that are sometimes relevant. For example, the algebraic degree, which is in this case 4 and in this case 2. So there are some cryptanalysis techniques which exploit when a function has a low degree, and there are cryptanalysis techniques that exploit when a function is close to a linear function. So this is a metric for nonlinearity. Now let's have a look at first a comment on choosing the number of rounds, and then a look at a metric that measures the diffusion, because this was a measure of the confusion. So for example, if the function is not very nonlinear, then if some of these bits are the key bits, they don't have a lot of impact and not a very complicated impact on the output, because it can be approximated by a very simple function, a linear function. So what can we say about the number of rounds usually? One strange thing in symmetric cryptography is that whenever you try to come up with any round transformations, you can, so no matter how silly they are, in almost all cases, you can actually use them to produce a cipher which is secure, given that the block and key size are sufficiently large. And to do this, you simply need a sufficiently high number of rounds, where sufficiently high can be something like 100, it can be something like 1000. That will depend a lot on what sort of function you use. But unless you choose completely weak functions, in many cases you can achieve this. However, the resulting cipher is extremely inefficient and very hard to analyze. So it's very hard to find out how many rounds you really need to achieve security. And so the central challenge in symmetric cryptography is to define a round function such that you have reasonable techniques to find out what a good number of rounds would be, what the sweet spot is that offers the strongest security, but also has a good performance. So you want the security to be strong enough to be above your limit, your threshold. So it should be every attack approach that exploits the round transformation should be at least as costly as the generic attacks. But it doesn't make sense to make it more complicated than that, to increase the number of rounds further, because it will only make the cipher less efficient, but not more secure. And ideally, you choose the number of rounds so that the security is a bit above the actual threshold, so that you have some security margin. In case the attacks get a bit better, you're prepared for that. But you don't want to do something like have 100 times as many rounds as you need. That would be wasteful and wouldn't be very trustworthy, because it would look like you don't really have any idea how strong your cipher is and how much you need to protect it, how many rounds. Okay, now as promised, a metric for the diffusion effect. So if you remember, diffusion was about spreading the effect of one small change at the input to more changes in the output. And a classical name for this effect that was first phrased by Horst Feistel, whom you know from the Feistel construction from designing the DES cipher. However, this avalanche effect definition is actually very close to what Shannon already defined for confusion. And what this avalanche effect says is we require that if the input to the cipher is changed slightly, for example by flipping a single bit, then the output must change significantly. So you will already notice this sounds more or less exactly like I defined diffusion. And that's correct. However, there is a more well-defined notion, a more specific notion, a probabilistic notion that makes it a bit more precise. And that was defined a bit later. And that is the so-called strict avalanche criterion. And this phrases the previous property more precisely by requiring the following. Whenever exactly one bit is flipped in the input, either from 1 to 0 or from 0 to 1, then if we look at one output bit of the ciphertext, the probability that this flips must be 50%. And this probability is taken either over the keys in case the attacker doesn't know the key, or when we look at the smaller function where the key is known, then this average or the statistical criterion is over all possible inputs. So if I look at all possible inputs and have flip a particular bit, then for all possible values of the plain text, flipping this bit must flip each output bit with a probability of 50%. So this does not mean that the plaintext bit only influences half of the bit, but it means that if I pick any bit, it must flip with probability 1/2. And I can't know in advance which it is. I have to try it out. So I really need to do this statistical experiment. So this strict avalanche criterion is a way of saying that each input bit first must influence each output bit. So each input bit must have the chance of toggling each output bit. And second, it also says that this chance mustn't be just irregularly distributed, like it only very rarely flips the bit, but it must flip the bit in 50% of all cases, taken over the ciphertexts and or the plain texts. And this is the strongest diffusion that you can get, essentially. So this is also behavior that you see, for example, when you look at hash functions. If you flip a bit at the input of the hash function, then half of the bits in the output will flip. And you can't predict which half of them, of course. There is a question, is it exactly 50% or at least 50%? That's a very good question. Maybe some of you can already answer it. There is no real answer, but just a follow-up question. Okay, so let's try to answer it. What would be if the probability that it flips is not 1/2, but larger? For example, if it would flip in 75% of all cases, isn't that great? Isn't that a lot more than 50%? Well, actually, that's pretty bad because it would make the output predictable. It would mean that if we flip one input bit, we can be almost sure that the output bit flips. So we could predict something about the output. This would be bad. So it should be as close to 50% as possible. And the follow-up question was what the acceptable error is. As very often in cryptography, the acceptable error is an error that is negligible. Negligible means the probability of the error is so small that I cannot measure it. Meaning, for example, if in a hash function, I take one of the output bits and let's say I have a hash function with 128-bit blocks. Then in the ideal case, if I flip the first input bit, then for half of the messages, so for 2 to the 127, the output would flip, and for the others, it would not flip. However, if the actual chance is not 2 to the 128 and 27, but 2 to the 126.5 or something like that, or 2 to the 127 plus 5 or something like that, then the error is so small that I cannot measure it in an acceptable number of samples. It's not distinguishable, is the terminology we have. And usually we say that something is indistinguishable or only has a negligible probability if the available data or the available time we have to execute a generic attack is not sufficient to be able to observe this difference with sufficient certainty. So usually the answer is if the error is something like 2 to the minus 128 or so, then we're good, because this is an error that is so small that all the available data we have is not sufficient to measure it in an acceptable time. So something like 52% would definitely be too much of an error. It's not an acceptable error. It's an error we can already measure if we only have something like 100 samples or so, or only 200. We can already be pretty sure that if we make 200 samples and 104 of them are positive, are a switch, then there is a good chance that this is a non-random property. How good the chances is a slightly more complicated statistical question. So if you want to put precise bounds on this, you need some statistics. But in general, anything that you can write down in percentages is a non-negligible error, an error that is too large. Whereas if it's something that you write as 2 to the minus a very big number, then it's usually negligible in our sense. So I hope this answers the question to some extent. So having an observable bias in there is always a bad thing. And actually that leads us more or less directly to some of the cryptanalysis techniques that there are, and in particular the one we want to look at today. So to give a bit of a broader perspective on cryptanalysis, one of the questions we should ask is, how can we be sure then that an attacker will definitely need a large amount of work to break a system, which is of course not perfect because it does have some structure? How can we be sure that an attacker still takes too long with every possible method there is? And the answer is, unfortunately, we can't really be 100% sure, but we can do our best in this direction. And all cryptography relies on doing our best and having a good understanding what this best is, so what the state of the art is. And in symmetric cryptography, this usually means we need to make sure that our cipher has a good security margin against all known attacks that we have, and also about variations that we could imagine of these attacks. So things that might potentially be possible, but we don't really know exactly yet how to do it. In asymmetric cryptography, we usually say we rely on a known difficult problem. Now, on paper, this makes it look a bit more secure than symmetric crypto, because in symmetric crypto, we just say we're trying to break it. And in asymmetric crypto, we say this is a known difficult problem. However, if we take a bit of a closer look, we will notice that the known difficult problem, like the factorization problem for a particular bit size, for example, is not actually that different from the case, for example, of AES. In both cases, clever people have tried for a long time to improve algorithms to attack them. And in both cases, there has been some progress, but not too much. Actually, there has been more drastic progress on the asymmetric crypto side than on the symmetric crypto side, at least since the introduction of AES or so. So in both cases, we try to find fast algorithms, efficient algorithms to attack the ciphers. And in both cases, if after a lot of effort we don't find anything, we say that we hope this achieves a certain security level. What I've said so far is particularly for the case, or is only for the case of mathematical analysis. Of course, there are also techniques for cheating, which are not a purely mathematical analysis of the cipher as specified on paper, but which take advantage of some additional properties, like sidechain law fault attacks. Now, since this lecture is on cryptography, I was not planning to go into much detail on that because there are other lectures, but what I can tell you is that the analysis techniques in some of those are extremely closely related to what we do in mathematical cryptanalysis. They're just a lot easier and more efficient to apply because we simplify the problem by cheating a bit. So for example, instead of having to attack the full number of rounds of a cipher, we just attack one round because we take a look inside with a sidechain or something like that. So in particular, what I'm explaining today is, for example, closely related to what happens in fault attacks, except that exploiting it is easier in fault attacks than in pen and paper cryptanalysis. So what cryptanalysis techniques are there? The short answer is very many of them. The slightly longer answer is there are very, very many, and if you just list different names of attacks, you would get a huge list. However, these are usually or very often related to each other. So we can sort of could draw a tree of different attack strategies that we know. And if we did that, then two big branches of this tree would be on the one hand statistical analysis, and on the other case, or on the other side, non-statistical attacks, so deterministic properties. And the difference between the two is that in statistical analysis, we're always talking about a slight bias existing in our cipher. For example, a particular output bit is more likely to flip than 50%. And we try to distinguish this bias. This is common to statistical attacks. On the other hand, we have non-statistical attacks, in particular the very large class of algebraic attacks, where we don't have this statistical methods, but what we instead have is some deterministic properties of the cipher. A particular example for algebraic cryptanalysis is when I'm describing my cipher in terms of precise equations. So I'm building up an equation system and then solving this equation system. Or I can guarantee a property like if I build up a particular set of plain text with these properties and these relations, then I can guarantee if I XOR up all the outputs, the result will be 0. That's an example of a deterministic property. So to evaluate it, I simply follow the exact instructions. I build up my set, I XOR all the outputs, I check if it's 0. If yes, then I've confirmed the property of the cipher. If no, then the thing I'm looking at is definitely not the cipher I thought. Otherwise, the property would hold. And in statistical attacks, there are two main classes. And actually, these two main classes are related to the two main properties we've defined so far. Differential cryptanalysis, which we want to look at today, is about predicting a difference in the output based on a difference in the input. So finding a bias in the output bit flips. There are a gazillion variants of this approach, like truncated and impossible and higher order and whatnot differentials. But they all follow some of the same basic observations. And this is related to the avalanche effect that we've described, which already said that if I flip a bit, the output should flip randomly. And differential cryptanalysis goes a bit further. It says that for every possible flipping pattern in the input, it should be hard to find any bias in the output flipping pattern. So it's a more complete description of what avalanche effect should actually mean for us. Not only if we flip a single input bit, but for all possible patterns that we could have. Linear cryptanalysis, on the other hand, is based on approximating a cipher based on linear functions. And this means it's related to the nonlinearity concept we heard earlier. So let's dive into differential cryptanalysis. This attack, as well as linear cryptanalysis, they were both proposed in the early 1990s. In the case of differential cryptanalysis, this was done by Beham and Shamir. You already know Shamir, that's the S in RSA. And it was later uncovered that the designers of DES, so in particular the NSA, actually knew about a slightly related attack a bit before that and took it into account when designing DES. However, this was never made public until way after differential cryptanalysis was published. And this, together with linear cryptanalysis, these are the two main attack techniques on block ciphers. And the attack, when executed, is usually a chosen plaintext attack because it always works by setting up pairs of plaintext which have a particular difference. So it always requires the attacker to be able to choose plaintext in some way. And the core idea is that you look at two input messages, M and M star or M prime. You consider the XOR between the two, which is called the input difference. and you want to predict something about the output difference from this. So a slight bias in the output difference, where the output difference is the XOR of the two corresponding ciphertexts, which I would get from these two plaintexts, both computed under the same key, but of course the attacker doesn't know that key. And so this is the one part to it. This is the so-called distinguishing property. And what we want to do at the end is we want to use this distinguishing property to then be able to discover something about the key. This is something that is in common to many cryptanalytic attacks. You usually find, that there are rounds. You try to find a property that covers as many of the rounds as possible. And then you try to come from the other direction, from the ciphertext direction, guess a part of the key, and then verify whether your prediction was satisfied. So you use guessing the key to confirm whether you can observe your bias, and if yes, then the key was probably correct. So to describe this in some more detail, let's have a look at a simple block cipher. And we're going to make this simple block cipher slightly more complicated in the next minutes to get further and further in the ideas of this approach. So our very first super simple block cipher looks as follows. We have some input block, we XOR a key to it. The result is called U, so this intermediate value here. And then we plug this into an S box. So our cipher is only defined for 4-bit inputs and 4-bit keys K0, so it has a 4-bit S box. The output is again XORed with the next 4-bit round key, and that's the ciphertext. And the idea is that the total key size here is 8 bits and the total plaintext size is 4 bits, as well as the ciphertext size. And the S box is simply defined here as follows, as a lookup table. So in total, there are 2 to the 8 possible keys here. And if I'm given some plaintext ciphertext combination, something that I can always do, a generic attack would be guess all possible keys and test whether with this key the plaintext matches to that ciphertext. And all keys that satisfy this are possible key candidates. Then in a second step, I would have to filter again until there is only one key candidate remaining. And with differential cryptanalysis, we want to do this a bit faster by taking advantage of differences. So instead of looking at just one plaintext ciphertext pair, where, for example, one plaintext value here would be 0xa and the other one would be 0x9. So these values here are always just hex representations of the 4-bit value here. And let's say our other plaintext ciphertext combination is 5 and 6. What can we learn about this, about the key based on this? So to do this, we need to look at the encryption processes of both our plaintexts in parallel. So we always imagine applying the cipher to both elements of our pair here. And then we trace through the execution of the cipher what the impact of the input difference is. So what can we learn from that? We are interested in the difference at the intermediate values U and V. What can we say about U if we start from this direction here? So the first U is computed as the first plaintext and the key 0. The second one as the second plaintext and the key 0, which is the same in both cases. Since it's the same and since we're XORing here, the two key additions cancel out here when I look at the XOR here. And what I'm left with is that the XOR between these two values must be exactly the same as the XOR between the plaintexts here. So in other words, the addition of the key here actually didn't have any influence on the difference. This is because if you take two different values and XOR the same value to both, then their difference will remain unchanged. If they were the same before, they will be the same afterwards, and if they were different before, they will be different afterwards. And we can say this, so we can say something about the intermediate results here without knowing anything about the key 0 at all. So this is when we come from this direction. What can we say coming from the other direction? And how can we use this in an attack? So the idea is as follows. First, I compute u0 from the left-hand side. This is easy, we just did that. And now I try to compute it from the right-hand side and see whether it matches. So let's start from here. I know the difference between the ciphertexts because I have them both and I can just XOR them. Then I have the difference. Now I go over the key addition step here. I actually don't need to know the key to learn that the definition in the V's is the same as the definition in the C's. However, if I want to compute further, so go back through this S box here, then I need to know a bit more. Because to be able to go backward through the S box here, I need to know the exact value here, meaning I would need to know the key. So what I can do is the following. I can simply guess the key here, so try through all possible values. And for each possible value of K1, I compute backwards in the decryption function of both of these ciphertexts. I will get a value of U0 here and value of U1 here, both of which are correct in case I guess the correct key candidate here. And if they were correct, then the difference I observe here must be exactly the difference I know they have when computing from this side here. So I'm guessing the key and then verifying my guess by checking if this property holds. Now, if this property does not hold, then I know my guess must have been wrong here. If it does hold, then this can be either because I had the correct key or by accident. Both of this is possible. But still, there will be many keys where the difference does not hold, and I can throw these keys away. They're definitely not correct. So instead of a loop over 2 to the 8 keys, I only used a loop over 2 to the 4 keys here in order to evaluate the property here. So I definitely have a process which is faster than brute forcing all key candidates. And this step here of throwing away the keys that do not work is also called filtering. So I'm filtering out wrong keys. And let's try to make this a bit more complicated. Let's first plug numbers in, apparently. Okay, let's plug numbers in. So we already have our plaintext ciphertext values from before. We can compute the difference of U0. So this is simply the XOR of the two plaintext values, so A plus 5. If I XOR these two, I get F. So I know that the difference must be F here. And now let's compute from the right-hand side. So I know the ciphertexts 9 and 6. And now for each key candidate here, K prime, I can now compute what the corresponding U's are. So let's first start here with the key candidate 9 here, 0 here. If the key was 0, then here we have a 9, so this must also be a 9. Now I can go backward through the S box by looking which input maps to output number 9. For this I need to scroll back a little. So output number 9 comes if the input is an E. So what we deduce then is, if this was a 9 here, then here must be an E. And similarly for output 6 here, I can go backwards, look what maps to a 6. Let's see, 0 maps to a 6. So this means we would have, what did I say, an E here and a 0 here. The XOR of those would be E. And this is what this table here also shows. And I can do this computation for all possible key guesses. And I will see that in most cases I will not get the right difference. There are only two candidates of K1, namely 7 and 8, which give us the correct difference at this point here. So the only candidates for the key that can be correct are 7 and 8. And if you actually check, then what you will notice is that 7 and 8 correspond exactly to the correct values V0 and V1 and the swapped values. Because if I swapped the two values here, then the difference at this place would be exactly the same. This is why I will always get at least 2 candidates here, because for any candidate, the swapped order of the values, which can be produced by a different key, would also look correct. So what I did is I used the fact that I can learn some information about the difference here without knowing K0, and that means that I only had to guess K1 in order to verify my guess here by computing backwards. And now if you compare this to more advanced cryptanalysis on more complex ciphers, what usually happens is that this part here is quite similar. So most differential attacks contain this part where I guess the last key here, or at least a bit of it, and compute backwards. But this part here is usually a lot more complicated in reality, because what we used here was a property that holds with probability 1. If we know the difference here, we know we are guaranteed what the difference after the XOR is. Whereas in actual attacks and actual ciphers, I usually cover many rounds here, and I usually don't have an exact knowledge of the difference here, but I just have a tiny bias. There is one difference which I know to be a tiny bit more likely than the others. And then if I observe, coming backward, this correct or this slightly more likely difference here, then the key is slightly more likely to be correct. What this means is that I must repeat this several times in order to confirm that this bias is actually what I measured and I didn't just get the difference by accident. So let's try to go a step in that direction and make our toy cipher a tiny bit more complicated, namely by having 2 rounds which each apply a single S-box. We use the same S-box as before. Now we already have 3 keys, so the total number of key candidates is already something like 4,000, whereas our attack previously only used 16 possible candidates here for K, for the last key. Let's repeat the same attack. Like before, I can compute backwards here by guessing the key K2. And here I want to do my match. If I look at the forward direction, the first step is easy, works exactly as before. However, now I need to cross this S-box here in the forward direction to learn something about this intermediate result here. And this I unfortunately cannot do in a deterministic way anymore. Here I need to take the properties of the S-box and say which difference is a bit more likely here. And the question is, we would want to verify our computed difference in V prime here based on the key guess. And we want to learn something about what is more likely to be the correct key here. So we want to, at this point, not take the same approach that we did in the backward direction. In the backward direction, we crossed the S-box by guessing the key. In the forward direction, we do not want to guess the key, but we only want to use the knowledge of the input difference here. So not knowing the exact values U0 and U1, just knowing the difference. So let's compute all the potential differences of V here. And we do this by making some computations of the S-box. So let's look at this example here. We're looking at all possible values of U0 and all corresponding possible values of U1. What we know is that the difference between the two is F, so we always XOR F to the one value to get the other value. And for each of these combinations, we can now derive what the corresponding values of V would be and have a look at what difference they would have. And if we do these computations, then we can observe the following. First, we see that not all difference values are possible for V. So for the output of the S-box here, if I know that the input difference is an F here between the two, not all output differences are possible. And we see that one of the output differences occurs a lot more often than the others. Namely, this value D here occurs really often. So this looks like a rather peculiar property of the S-box. In 10 out of the 16 times, we got the same output difference. So when we're an attacker and do this attack, it would be a good guess to say, the difference in V is probably D. And with a probability of 10 over 16, we are correct. So we can use this to filter some wrong key guesses. For this, we will not just use one plaintext ciphertext pair here, but actually a higher number. So in this example here, we are using 16 plaintext ciphertext pairs, all of them with an input difference of F. Then for each of these 16 pairs, we compute backwards from the ciphertext we have under each possible guess of the key K2. And now for each of the pairs we have, we compute backwards here, compute these intermediate results X and W, and count how often we observe here the difference that we would expect. For the right key, we will always get the right result here, and we know that the right result has a difference of D with a probability of 10 over 16. So for the correct key, we will also observe approximately 10 out of our 16 pairs will satisfy the correct difference, or our favorite difference D, whereas the probability that D shows up here for a wrong key is only by random chance. So for a wrong key, we think that the probability of having a difference D here is approximately 1 over 17. So on average, one pair would have our favorite difference here. So we see that the behavior we expect, or the observations we expect for the right key and for the wrong key are quite different. And our job as an attacker is now to distinguish these two cases. In the present case, this looks very simple, because if I observe the value D something like 8 or 9 or 10 or 11 or 12 pairs, then the reason is probably because we had the right key. Whereas if we observe something like 0 or 1 or 2 or 3 matches, then we can be almost certain that this was the wrong key. So the right key and wrong behavior are quite far apart. And this is just some reasoning why the expected probability is 1 over 16 for a wrong key. This is simply the average behavior. So this is under the assumption that the behavior under a wrong key is approximately random. This is also called the wrong key randomization hypothesis. So on the previous example, we already had this input difference pre-selected. So we were given a plaintext ciphertext pairs with F as an input, and we saw that D was a good output. Now, in general, if we don't have this F given, how can we find a good probability? What should we have a look at? And the idea is that we look at all possible input differences for an S-box and check whether there is any particular bias visible in the output. So what we do is, for every possible input difference U, delta U, we compute the corresponding output differences delta V for all possible values of X. So we look at the following equation. We XOR the S-box of the input value and the S-box applied to this input plus the difference. So in other words, this is the second input value in this pair of input values. And we XOR the outputs to get the output difference. So this is simply an equation writing down what we saw in the previous pictures with an input difference and an output difference between input and output values. And we can write this, the number of solutions to this for every possible input difference and every possible output difference down in a table. And this table is called the difference distribution table, or differential distribution table. So it has 2 to the n times 2 to the m inputs, where n is the number of input bits and m the number of output bits. Usually both are the same. And in each entry of the table, we write down how many solutions this equation have. So how many input values map this input to this output. And we get a table like this. So here's, for example, the value of 10 that we saw in our example. This was for an input difference of f and an output difference of d, like in our example. And here we said in 10 cases this was satisfied. We see that most of the cases are satisfied in 2 or 4 solutions. A dash means a 0, which means this is not possible to go, for example, from 4 to a 0. We also see one other very high number here. But that's not really surprising, because what this says here is that if the two inputs have a difference of 0, in other words, if the two inputs are the same, the outputs are always also the same. And this is not really surprising, because the S box is deterministic, right? Same input in, same output out. And you also see, for example, that no other output is, of course, possible if you have a 0 input difference. So the first row and the first column of the difference distribution table is always all zeros except for this high entry here. And what the number here means is that the probability that this input maps to a particular output difference is the number here divided by the number of possible inputs. So for example, the probability that an input difference of f matches to an output difference of d is 10 out of 16. And we can now evaluate the S box based on this, on the largest entry in this table here. So of course there's always this one here. We don't count it because every table has it. But this one here is the most interesting property, or the most interesting combination of input and output difference. And we call this maximum entry in there the maximum differential probability. And it's simply defined as the maximum probability of any non-zero input difference to be mapped to any output difference. So with this non-zero here, we're excluding the top left entry. And this differential probability of input to output difference is exactly what I just explained. Here it's just written down as a formula. So it says that the probability is the number of solutions to this equation divided by the number of all possible inputs, 2 to the n for an n-bit function. So in the previous example, this maximum differential probability was the largest entry in the table, 10, divided by the total number of possible input values, 2 to the 4, which is 16. So 10 divided by 16 is the maximum differential probability of this S box, making it a very bad S box because this is such a large value. Maybe a short comment here. What would be good values at this point? Well, the smaller the better. What is the smallest possible that we can get here? Any ideas in the chat maybe? What is the smallest? So if we try to make our S box as good as possible, what is the minimum possible value for the maximum entry in the table? There's already one guess in the chat, which is that 1 would be a solution. Does everybody agree to this? So is it possible to have a table which has no larger entry than 1? Any opinions? No opinions are forthcoming, so maybe I can answer that. If you look at the table here, 1 doesn't quite work out. So it would be what we would ideally like to have, because it would mean that every output value occurs with the same uniform probability of 1 out of 16. That would be great, would be the best we could hope for, but it doesn't really work out. The first reason for this is that we already said that the first column here always has all zeros, which means there are only 15 entries left in each row where I can put my 16 cases. Now, by the pigeonhole principle, there must be at least one entry here which has a 2. Otherwise, it doesn't work out. It can't sum up to 16 when I only have 15 available slots. That's the first reason why 1 doesn't work out, and there is another reason why it doesn't work out. And that is, you can already see here that all the entries are even numbers, divisible by 2. And we already mentioned this a bit earlier. We said that if there is one input solution that maps this input difference to this output difference, there is always at least one second one, which I get by simply changing the places of the two values. So for example, if the values 2 and 3 are two possible values with input difference 1 that map to output difference 1, so if 2 and 3 is one solution, then 3 and 2 must be the other solution here. I can always find a second solution. So all entries are even, so 1, which would be our dream come true, unfortunately won't come true, and the best possible we can achieve here is a 2. 2 divided by 16 in case of 4-bit S-box. Unfortunately, in the case of 4-bit S-boxes, there is actually no S-box that satisfies this ideal value, and we need to have at least a 4 here. So we don't quite get as low as we would like, unfortunately, which means that the S-box always has a particular bias in a certain direction. There are always some output differences which are a bit more likely. And the question is, how can we get rid of this bias? And the essential approach is to consider not just one round, but several rounds. And to look at the probability that a particular difference happens not just after one, but after many rounds. And this way, if the first round still has a bias, then this bias is smudged a bit in the second round. Because so the probabilities essentially multiply up here. And the more rounds we do, the smaller the overall bias becomes. So we need many rounds to get this, to get rid of this bias that the S-box always has to have. And in the end, if we look at the full cipher, what we would like to have is that an attacker cannot find any differences that are more likely. So in particular, if we would write this as one big, huge S-box, there always must be some slightly more likely values. But since this depends on the key, what we would like to have is that for an attacker, it looks as if the big distribution table from here to here had all ones in it, which of course it doesn't have for the reasons I just explained. However, we want it to look like that for an attacker. So we want it to look exactly like Michael suggested. And the strategy of an attacker to still execute a differential attack is now to try to find still a good pattern, also difference to difference transition with a good probability. And usually we describe this in terms of a characteristic. So a characteristic says not just what the input and the output difference after, for example, 3 rounds are supposed to be, but it gives me an intermediate result for each round. So we have a possible transition from delta 1 to delta 0 to delta 1, and another possible transition from delta 1 to delta 2, from delta 2 to delta 3. And this way we have one possible path where each step has a particular probability. And if I multiply them all up, then I have the probability that a difference, an input difference here goes to a particular output difference here, following this particular pattern that I described here with the characteristic. So this is the differential characteristic, such a pattern or such a path of intermediate differences. And the general attack strategy is then, if I have found a good characteristic, then I try to repeat the approach from before. I collect many pairs with the right input difference. I look at the corresponding ciphertext values, guess all possible values of the fourth round key, compute backwards, and count how often I observe my favorite value delta 3 here. And if I observe it more often than by random chance, then this is a good indicator that my key guess was correct. Okay, and this attack here, this approach only works if the probability here is sufficiently high that I can measure it. So in particular, what I need to have is that the probability of this so-called differential here, so a combination of an input difference and an output difference is called a differential. The probability of this differential is a lot bigger than what I would get by random guessing. So the random probability that a particular difference occurs is 1 divided by all possible options, so 2 to the minus n. And if I have a characteristic which has a better probability than that, so higher probability, then it's something I can hope to distinguish because it looks different from the random case. This is what I try to do. Something that is more likely. So for example, if we look at this 4-round toy cipher here, which is now a bit more complicated. So we have not just one S-box per round, but 4 of them. And we also have a permutation layer for mixing, where the 4 output bits of the S-box are distributed to different S-boxes for the next round. And here is, again, the S-box that I'm using. And here is a specification of this bit permutation here. But we can also just follow the picture. So the most important thing to notice about this permutation here for the following is that for each S-box there is one bit which remains in the same place. So here it's the most significant bit, here it's the second most significant, here it's the second bit from the right, and here it's the least significant rightmost bit. Okay, so to find a good characteristic for this, we need to do 2 things. So first, we need to find good transitions for the S-box by setting up the difference distribution table and finding high entries. And the second thing is to try to fit the pattern we find here in some way that it integrates well with these permutations. So in particular, one of the patterns that satisfies this is the input difference 0020 and the output difference 0020. The probability for this to hold is, the claim is here 6/16. To understand why this is the case, we need to scroll back a little, back to our difference distribution table, and have a look at the difference transition from 2 to 2. We see that the entry here is 6. So the probability that a difference of 2 is mapped to a difference of 2 is 6/16. And now if we have a look at the picture of our cipher here, let's say we do an input difference of 0 here, 0 here, 2 here, 0 here. Maybe I write that down in case the thing here chooses to cooperate. So we have 0 here. Pen is not working, so we have, sorry for the handwriting, 0 here, 0 here, 2 here, and 0 here. And we look at the output difference in the lookup table. If the input difference is 0 here, then the output difference is definitely also 0 here, because same inputs, same outputs. And same thing here and here. And for 2, we said that the output difference is also potentially 2, and this is with a probability of 6/16. Now 2 means that exactly this bit here, the second bit, is active, and here also. And if we look, this is exactly the bit that stays in the same position. So if we look at this input pattern on top here, then what do we get on the bottom? The only active bit here is this output bit, and all the other bits here are 0, meaning we get at the output 0, 0, 2, 0. And this is exactly what was claimed on the next slide. And the nice thing here is that if we have found this property for one round, we can see that we can also repeat it for the next round, because the key addition here doesn't change anything. So we again have 0, 0, 2, 0, which means here we again have 0, 0, 2, 0 with a probability of 6 out of 16. And again after the next round, so at the end again 0, 0, 2, 0. So for this part here, this works deterministically because the active bit here stays in the same place. And the S box here is what does the probability. Here another 6 out of 16, and here another 6 out of 16. And here we have 0, 0, 2, 0. And this is nonsense. This shouldn't be part of the cipher. So what we have found here is a differential characteristic with a probability of 6 divided by 16 to the power of 4, because for the complete path to hold and all the intermediate differences, we need that the first and the second and the third and the fourth transition holds. And to do this, we simply multiply up the probabilities. Okay, so this means this is our characteristic and this is our probability of the characteristic. And here is a text explanation of exactly what I just showed. So in total for 4 rounds, the probability is 6 divided by 16 to the power of 4, which we can evaluate and get 81 out of the total of 4,096 cases. And one thing to notice here is that in the picture here, we've prescribed a particular path to take. So we've prescribed not only the input and output difference, but also all the intermediate differences. And of course, in reality, this might not be the only possible path. So it could be that there is a second output value here in this part here, which doesn't match to 2 here, but distributes the differences a bit, but which still leads back in the end to 0, 0, 2, 0. So it could be that the actual probability of observing 0, 0, 2, 0 here is a bit bigger than this one here. It can't be less, because we already have found this one possible path. This is definitely possible. However, it can be higher. For an attacker, this means that the attack can always be a bit easier than expected, because the bias could always be a bit bigger than expected, but it cannot really be less than expected. So this is nice for the attacker's perspective, because the attack might be unexpectedly easier, but for the designer, this is of course unfortunate, because the best attack might always be a bit better than the designer thought. So this is a reason to take a bit of security margin into account. And in the particular case here, if you evaluate it, then the 4-round differential, which means this input to this output, but we don't care about the intermediate differences, actually does have a much higher probability, namely about 4 times as high as we thought. So for what this could mean is, for example, that there is a total of 4 paths with the same probability as this one. That would be one possible explanation why in reality this is high. But of course, finding out this real probability is a lot harder than finding just one good characteristic. But if we want to defend against this type of attack, one approach that we can do is we can try to make sure that there is no individual characteristic with a high value here. And then we add some security margins so that we hope that the best actual differential probability isn't too much higher than that and is still too small to be used for an attack. And that's the essential defense strategy against this attack, making sure that the best characteristic has a low probability. And if we revisit again what this probability depended on, we see that the main source for the the main influence on the probability was the choice of the S-box. Because in each round we had this one active S-box. We say that an S-box is active if it has a non-zero difference. And we saw that every S-box contributed this probability. And if the S-box would have been better, then this probability would have been smaller. And this smaller probability would have had a lot of influence on the final result, because the probability is taken to the power of the number of times we use it, that transition. Okay, so let's have a look at how the AES defends against that and what the white trail strategy includes. So what we want to make sure is that each possible characteristics has a probability as small as possible. And what we hope for is that in consequence, the differential also has a low probability. And of course, it is a bit difficult, or it is difficult to evaluate the best possible differential. So what we usually do is we derive bounds, so limits on the probability of the best available characteristic. So when we design a cipher, we want to make statements such as we can guarantee that the probability of the best characteristic is no more than this and that. It might in reality actually be lower, but it can be as most as high. And this is done in 2 steps in the case of the white trail design strategy. We've already hinted a bit at what the first step is, namely to look at the S-box and to make sure that there are no big numbers in the S-box. Because a high number in the S-box means a high bias, which is easier to exploit. And the second thing we take into account is how many of the S-boxes are activated. Because if more S-boxes are activated, I need to multiply more times this probability, and the more often I multiply numbers less than 1 with each other, the smaller the overall result gets. So if more S-boxes are active, then the total probability that I get is lower. And so the 2 ingredients to the design strategy is to first make sure that the maximum differential probability is low, and second, that the mixing layer results in many active S-boxes. In the previous example, we had exactly 1 active S-box per round, but we will see that we can do better than that. So these are the 2 main ingredients of the white trail design strategy, where white trail means, so trail is another word for a differential characteristic, and white means it's not just one narrow path that has just 1 active S-box per round, but we want to have more per round. So it's broader in the sense that it has more S-boxes in it, and more S-boxes means lower probability. So let's first have a look at what we can do to a single SPN round to improve its resistance. So what's relevant here for the number of active S-boxes is the number of active, where is my mouse going? Here. So what's relevant is the number of active cells in the input, where a cell is one of these input values to the S-boxes here. And what does this mean? What is the highest probability that I can get here over 1 round? Well, the probability is higher if I have only 1 active S-box, for example, the rightmost here. And if the transition that I pick here is the one that matches the maximum differential probability from the table. So in total, the best probability I can get for 1 round is exactly the value of the maximum differential probability from the table. And we can see here that if we just look at 1 round, then the mixing layer doesn't really have an influence yet. because it will only distribute the individual bits here of the S-box output to different places, but this does not yet influence the probability. The only thing that influences the probability is the one active S-box. But the importance of this mixing layer becomes visible as soon as we look at more rounds, namely at 2 rounds. So what is relevant here for the total cost? The relevant question is how many S-boxes are active in the first round and how many in the second round. So in total, we're interested in how many of these arrows here, where one arrow represents multiple bits, however many bits go into the S-box. How many of these blocks have a non-zero value? Because if I have a 0 value, then the S-box maps it to a 0 difference with probability 1. And how many I have here and here as of before and after this P layer combined depends on the behavior of this mixing layer. In the previous example we had, this mixing layer was very simple. So we had this example where we had a difference of 2 to 2, and we saw that this one active bit here was mapped to just one active bit in the next round, to also give us a 2 again here. But if we define a more clever layer, where, for example, one bit here gets diffused to different bit positions, we can make sure that after the mixing layer, there is more than one active block. And this is the idea of the branch number, or B. And this branch number is a property of the mixing layer, and it tells us the minimum number of active S-boxes in 2 consecutive rounds. So it provides a lower bound on the number of active S-boxes per 2 rounds. And it's a property of this mixing layer here. So what is the best possible that we could get here? If we have a construction like in the AES, where we have, for example, the state structured in bytes, so each arrow here would be 1 byte. We also say that this is a cell or a component. Then what would be the best possible behavior of the permutation layer? What is the best value that we can get for the branch number? So the ideal case is, of course, if I change just one value here, ideally we would like that it influences all of the outputs of the permutation layer. So the number of these components here is based on the size of the state. So in this case, it would be 6 and 1 here. So in total, here we would have 7 active bits if we had this ideal construction of a permutation layer. Of course, there are also other possible combinations. So if we want to satisfy a branch number of 7, it's not sufficient that we just guarantee that one change here influences all at the output. We also need to guarantee, for example, if I activate 2 values, it must also guarantee that all except 1 at the output are activated. If it's fewer, then my branching number is also smaller. So I need to guarantee to achieve this ideal number, I need to guarantee that whenever I take L active elements at the input, then there are at least, let's give a name to this number of components here. Let's say this is called, I don't know, M. We need to guarantee that at least M minus L plus 1 elements are active here at the output. And this would be sort of the ideal mixing layer. And it is actually possible to build such mixing layers which guarantee that. And if they do it, we call them MDS mixing layer, where MDS is short for maximum distance separable. This is a term from coding theory. And it gives us exactly the property that we need here, namely that we guarantee that if we take the inputs and the outputs together, in total at least 1 plus m elements of the input and output together are active, which means over 2 rounds we always have at least 1 plus m many active S boxes. So how does the AES implement this strategy? So let's look at the different operations of the AES. If you remember, AES came in different variants. We were mostly focusing on AES 128 here. And it has a certain number of rounds, which depends on the size of the state. Let's focus on this variant here. And let's have a look at what the individual components of the AES do to achieve a low differential probability. So the first step, or actually the last step in the round operation of AES, is pretty straightforward in this regard. This is simply the key addition step. It's simply the step that makes the entire function, the round function, depend on the key. So it doesn't really do a lot for our differential cryptanalysis here. But let's now look at the other operations. First, the S box. So this is an 8-bit to 8-bit S box. And it's actually defined not in some random way, but in a very specific algebraic construction, namely by implementing the multiplicative inverse over this particular finite field here. As a reminder, we're going to cover finite fields in more detail in one of the later lectures. So for now, let's just stick to this short description here. But the important property is that this particular construction using the multiplicative inverse guarantees that the maximum differential probability of the S box is exactly 4 out of 2 to the 8, meaning that the biggest entry in the differential distribution table is 4, which is very small. Ideally, we would like to have 2s only. This would be the best case, but unfortunately, we currently do not know any 8-bit S boxes that satisfy this. But the 4 is the next best thing, so this means that AES uses the best S box that we know in terms of resistance against differential cryptanalysis for 8 bits, which has this maximum entry of 4. Looking back to the properties we defined in the beginning, the AES S box also has a very high nonlinearity. So this nonlinearity is 112 out of 256, which is approximately 7 over 16. And this is a very good value. How can you tell that this is a good value for nonlinearity? You can see that the number on top here is approximately half of the total number of cases. And we cannot really get better than half of the total number, because if we would be significantly above that, then we could find another good linear approximation by simply flipping all the bits. So the best possible distance of a function from a linear function would be if it's wrong in exactly half of the cases. If it's wrong in more than half, then flipping would make it into a better approximation. So being close to 1/2 is the best we can hope for here. And here we are really close to half. You can also see this here. So this is the same as 8 minus 1 over 16, where 8 would be 1/2. Okay, so both the nonlinearity of the AES S box and the differential probability are really strong in this operation. And this was also the main reason for choosing this S box. There are a few constructions that we know of that achieve these numbers, but not very many. Next, let's have a look at the shift row step. So at first glance, this doesn't really seem to do much because it simply shifts the bytes around. The point of this operation will only be clear when we look at the next operation, namely at mixed columns. If you remember, mixed columns work by taking a column of the AES state, multiplying it with a matrix, and overwriting the result with that. And the matrix here is again defined over the same finite field. Now the good news about this matrix, about this specific matrix here, is that it satisfies a branch number of b equals 5. If you remember, we said that the best possible branch number is the size of the thing plus 1. So the size here is 4. So 4 plus 1 equals 5 is the best possible branching number that we can get within one column. So AES has chosen a mixing step that has the best branch number within a column, but it's worth noting that it did not pick the overall best. So instead of doing this column by column operation, we could have also done a linear full state to full state transformation. And in this case, we would have received a higher branch number, because the branch number would have been 16 plus 1, 16 for the total input size plus 1 for the optimal branch number, so it would have been 17, which is better. However, such a function would have been a lot more expensive to evaluate. So what AES chooses to optimize for is not the 2-round behavior, but the 4-round behavior in relation to the cost. Because for the 4-round behavior, you can notice that if you look at the interplay of mixed columns with shift rows, you see that all the outputs of mixed columns in one round are distributed to different columns for the next round. So this shift row step here serves to diffuse the effects of mixed columns to all the other columns, which means that while the AES doesn't achieve a very high branching number over just 2 rounds, speaking for the full state, it does so over 4 rounds, because you can imagine this as like a meta construction. If we rewrite the cipher as 2 rounds on top, 2 rounds on the bottom, and a strong mixing layer in between, which is composed of this optimal diffusion layer here in the middle between the second and third round. Then this meta mixing layer activates a total of 5 meta boxes, which consists of 4 S boxes each. And within each of these meta boxes, which are also called super S boxes, we have the 2-round property of having at least 5 active S boxes. So in total, we have 5 times 5 equals 25 active S boxes. If this explanation was a bit too fast, then that's because it was intended to be. So the detailed explanation is not part of the lecture here. We usually do that in the follow-up lecture in cryptanalysis instead of cryptography. Okay, but this is the design principle behind mixed columns. Its main purpose is to achieve this branching number. So in particular, this matrix is a so-called MDS matrix, maximum distance separable. So what does this mean overall? Here is an example of a pattern for characteristics for 4 rounds of AES. What I've illustrated here is in each state I've drawn all the state cells, so all the bytes with a 0 difference, I've left them in white. And whenever there is a colored box, it means that the byte has some difference. I have not specified which ones, but it has some difference. And everything I've marked here in red is an active S-box layer. So if I start with just one active cell in the state in the beginning, and I go into the first S-box layer, then one S-box will be active here, meaning the output also has a difference. If I now look at the mixed column step here, I know that because of the branch number 5, this one difference must be blown up to a total of 4 differences here, which means that in the next S-box layer I have a total of 4 active S-boxes. These are then distributed to different columns in the shift row step, and each of these columns blows up to a fully active state, again because of the branch number. Meaning that when I go into the third round, I already have a whopping 16 active S boxes here. Now, if I'm very, very lucky, then each of these active columns here at the input of the third round mixed columns will map back to just a single active cell here. This is if I choose all the differences in a clever way. It isn't guaranteed to happen, but it can happen. And in this best case, then I have again only 4 active differences in round 4. So in total, I have 1 plus 4 plus 16 plus 4, which equals 25, exactly as promised, as the number of active S boxes in 4 rounds. Now, this is not the only pattern that satisfies this. There are also several other ones. So, for example, you can also start in the beginning with 2 active S boxes here, then you only get 3 here, and the exact pattern looks a bit different, but you never get below 25 active S boxes. And what does this mean for the probability of the best characteristic? This means since we have 25 active S boxes and each of them has this wonderful maximum differential probability of only 4 out of 16, it means that after a total of 4 rounds, the overall probability of the best characteristic can be at most 2 to the minus 6 per S box times, so to the power of 25 S boxes, which is in total 2 to the minus 150. And this probability is a lot smaller than 2 to the minus 128, which would be the probability of randomly observing a particular output difference. What does this mean? It means that the knowledge of even the best characteristics does not help me at all in improving my guesses for what the output difference is, because I would be better off by just random guessing. This means that already 4 rounds of AES have a strong resistance against differential cryptanalysis. And the total Cipher with a total of 10 rounds is by far sufficient to protect against this type of attack. Okay, that leads me to the conclusion. We saw that design approaches in symmetric cryptography are in a way bottom-up, in the sense that you try to start from simple components which do not have much security, like just the S box by itself, but you combine them into something that has in total stronger properties. So you build a product cipher. And the goal that you have is you try to build something which you cannot break with state-of-the-art cryptanalysis. And one of the main techniques for this is differential cryptanalysis, where the attacker tries to find high probability characteristics to learn some tiny bias about the output, which would help them in confirming their guess of a partial key. Whereas what the designer tries to do is they try to prove that no good characteristic exists. Now, you cannot generally prove that you are completely secure against differential cryptanalysis because of many reasons, including the fact that we always talk about characteristics, but what we actually exploit are differentials, and a differential contains potentially many characteristics, and it's very hard to analyze that. However, if you show that first, the best characteristics are still really bad, and second, for example, by doing experiments, you show that not too many characteristics contribute to the same differential, then you have good arguments for security against this attack technique. And in the end, what you always try to achieve is you try to weigh and find a trade-off between having reliable security arguments, trustworthy security on the one hand, and a good performance on the other hand. Okay, that's essentially my summary of today's lecture. As usual, I will upload the corresponding exercise sheets either later today or tomorrow. Do you still have any questions for me at this point? That doesn't seem to be the case. Sorry for having a not very interactive lecture today. This is because there was just really too much stuff to cover, and we barely managed in the time without any quiz or anything. If you have any preferences for how we should do that the next weeks, let me know. In the meantime, I hope you have a very nice weekend and see you again next week.